Hi, this is Mrs. Basin, and today we're going to talk about how to calculate empirical formulas. So just as a quick review, when we're talking about formulas of compounds, formulas represent the relative numbers of various types of atoms present. So it tells us the elements or the atoms that are in a compound. There's a couple different types of formulas that you can use. So the first one is called an empirical formula. This tells us the smallest whole number ratio or the relative number of atoms present in the compound. So what is the ratio of all the atoms that are in that particular compound? The molecular formula tells us the actual number of atoms of each element in the compound. So it's not necessarily the lowest whole number ratio. The structural formula is something that we'll come back to later on. Those use lines to represent covalent bonds, and it shows us how the atoms in the molecules are connected or bonded together. So it gives us a little different type of information. So you can see a comparison here. So if we look at benzene, you can see the empirical formula is just CH. So the ratio of C's to H's is 1:1. The molecular formula, or the actual formula, is C6H6. And then that structural formula shows you how all of those atoms are connected. So really in all those three, that structural formula gives you a lot of information, and it helps you visualize what that molecule looks like, or that compound looks like. The next one is acetylene. So you can see the empirical is CH. The molecular is C2H2, and then it shows you how those are bonded together. Same thing for glucose. And then for that last one, ammonia. So what we're going to focus on for now is the empirical formula and the molecular formula, and then later on we'll come back to those structural formulas. So let's start by looking at molecular formulas and using the molecular formulas to come up with the empirical formulas. So in each one of these, it gives us the molecular formula, and we want to try to figure out what the empirical formula is. So the first one is C6H6. So this is called benzene, and we actually just saw this on the previous slide. So this is something that's used as a starting material for a lot of products that are produced in industry. So we're going to look at the molecular, which is given. And to get to the empirical, we're looking for the lowest whole number ratio. So we're looking to see basically if we can reduce those subscripts. So we could divide both of those subscripts by 6, and you would end up with CH. Another way to write this is you could write it this way and show that that 6 actually goes on the outside. If we're looking for a true empirical formula, this would be the empirical formula. You'll see later on when we go from empirical back to molecular that we'll come back to this notation here. Okay, our next one is a substance called dioxin, which is a poison that can be a byproduct of some chemicals. So this is C12H4Cl4O2. So again, we're looking to see if we can reduce those subscripts. So all of those subscripts could be divided by 2. So then my empirical formula would be C6H2Cl2O. So I'm dividing all of those subscripts by 2, and that would then give me the empirical formula. So again, the actual formula, if you actually looked at that molecule, it would have 12 carbons, 4 hydrogen, 4 chlorine, and 2 oxygen. But if we're just looking for the ratios, the ratio is 6 carbon to 2 hydrogen to 2 chlorine to 1 oxygen. Okay, the last one is the formula for nylon, or one of the reactants used to make nylon. So C6H16N. And for this one, there isn't anything I can divide all of those by. So this one, the empirical formula is actually the same as the molecular. So it is possible that the molecular and the empirical formulas are the same. So when we do lab analyses of compounds, it doesn't often give the chemical formulas directly. What it does give you is the relative masses of each element present in a compound. So then if you know the relative masses of each, you can go through a process to figure out what the empirical chemical formula is. And then later on, we'll come back and add on another step that then allows us to get to the molecular. But for today, we're just going to focus on how to get to the empirical chemical formulas. So to do that, we have to have the relative masses. So it's going to give you percentages of elements in a compound, or it's going to give you grams of element in a compound from an analysis. So what you do is you assume you start with 100 grams. So if it gives you a percentage for each one, you make that percent grams of each element. Sometimes they'll give it to you in grams to start with, and you won't have to do that. Then you're going to convert grams into moles using the molar mass of each element. You're then going to divide by the smallest number of moles. Then you're going to look at that final number that you came up with. If that answer is within 0.1 of a whole number, then you can round it to a whole number. If it's not within 0.1, then you have to multiply all of those numbers by some number to get to a whole number. And there's kind of a little cheat sheet there that you can use when you're multiplying. So this sounds a little bit confusing. The best way to do this is to go through and do some practice problems. So basically you're starting with grams, converting grams to moles, dividing by the smallest. At that point, if you have a whole number, you're done, and those are your subscripts. If you don't have whole numbers, you then have to multiply by some number to get everything into whole numbers, and then those are your subscripts. Okay, so this one says we have a compound that has nitrogen and oxygen, and it's decomposed in the lab. It produced 1.78 grams of nitrogen and 4.05 grams of oxygen. So calculate the empirical formula. So it went through the analysis, it was decomposed, and those were the two amounts of elements that were in that compound. So we're going to use those amounts to figure out what the formula of that compound is. So we're going to start in a similar way to what we've done before, where we're going to list the elements in the compound, and then we're going to list the grams of each. So 1.78 grams of nitrogen, 4.05 grams of oxygen. Okay, so then, and these were already in grams, so we didn't have to take the percents and change them to grams. Okay, so they're in grams first. So next step is I'm going to convert grams to moles using the molar mass of each element. So nitrogen is 14.01, oxygen 16.00. Okay, now at this step, it's important to leave lots of decimal places. So I'm going to leave, or you could even think of it as leaving like 4 sig figs. So I'm going to leave 4 decimal places on this. And this is important because this makes the numbers easier to deal with in the next step. So for nitrogen, that's 0.1271 moles of nitrogen and 0.2531 moles of oxygen. Okay, so I started with grams, converted to moles. Now my next step is to divide by the smallest of the moles. So in this case, smallest moles is nitrogen. So I'm going to divide both of these by nitrogen's moles, because again, I'm looking for the smallest whole number ratio. That gives me 1 for nitrogen and 1.99 for oxygen. Okay, so this one's good. This is within 0.1 of a whole number, so that means I can round that to 2. So then those 2 numbers in the box, those are my subscripts that go next to my elements. So then for this one, my final formula would be NO2. So the 1 I don't need to write, so there's 1 N and 2 O's. So this would be the empirical formula of that compound. Okay, so here's another one. This one says find the empirical formula of a compound that's 48.38% carbon, 8.12% hydrogen, 53.5% oxygen by mass. So again, I'm going to make a list: carbon, hydrogen, and oxygen. So those are the 3 elements that are in that compound. Carbon, 48.38 grams. So this is where these percents, I'm going to assume 100 grams, so I can just make those grams. So 48.38 grams of carbon, 8.12 grams of hydrogen, 53.5 grams of oxygen. Okay, so I have grams first. Now I'm going to convert to moles using the molar mass. So 1 mole of carbon is 12.01 grams. 1 mole of hydrogen is 1.01 grams. 1 mole of oxygen, 16 grams. So then that gives me 4.028 moles of carbon, 8.12 0.040 moles of hydrogen, 3.344 moles of oxygen. All right, next step, divide by the smallest. So I'm going to look at those 3 moles. The smallest is oxygen, so I'm going to divide all 3 of them by oxygen's moles. Because again, looking for the smallest whole number ratio. Okay, so I know this is going to give me 1. If I take 4.028 divided by the 3.344, it gives me 1.20. This one gives me 2.40. Okay, so at this point, this is not within that 0.1 of a whole number. So I have to multiply by some number to get to a whole number. So that's when I can go back and reference that chart that was on one of those previous slides. So if you have something that is a 0.2 to get to a whole number, I can multiply by 5. If I have to multiply one thing, I have to multiply them all. Okay, so I'm going to multiply all of these by 5. So then that gives me 6 for that one, 12, and 5. So then those become my subscripts. So formula for this one is C6H12O5. Okay, so again, this is the subscript for carbon, subscript for hydrogen, subscript for oxygen. And the reason I had to do this extra step was because at this point, those were not within 0.1. If they're within 0.1, you can round. So you can, if it's 0.1, you leave it at what it is. If it's 0.9, you round up. But any other decimal, you have to refer to that chart and see what can you multiply by to get to a whole number. And again, whatever you multiply one by, you have to multiply them all by. And we'll do lots of practice with that in class so you get the hang of that. Okay, last example. This one is for ethyl butyrate. So this is a compound that's found in natural pineapple flavoring. So this is the empirical, or calculate the empirical formula of ethyl butyrate. So it has carbon, hydrogen, and oxygen in it. And it gives me the amounts of each. And again, my percents, I'm going to just make those grams. So 62.04 grams of carbon, 10.41 grams of hydrogen, 27.55 grams of oxygen. So I have grams, convert to moles. So 1 mole is 12.01 grams of carbon, 1.01 grams of hydrogen, 16 grams of oxygen. Again, I'm going to make sure I leave plenty of decimal places here at this next step. So 5.166 moles, 10.307 moles, and 1.722 moles. Now I'm going to divide by the smallest. So this is my smallest. So I'm going to divide all of them by that. Okay, so when I divide that first one, it's going to come out to be 3. For hydrogen, it comes out to 5.99. So that one's okay to round to 6. And this last one is going to be 1. So this one I don't have to do that extra step because they all round. So then my final formula is C3H6O.